Okay, so we're starting the non-standard normal distribution. This is just more bell curves, uh, but but now non-standard means the mean is not 0 and the standard deviation is not 1. When the mean is 0 and the standard deviation is 1, that happens after you take z-scores. But what about before you take z-scores? Well, those are non-standards. It just means you haven't standardized yet. The first step with any distribution is to standardize it. And so you start with your population, take z-scores, and then look up probabilities is basically the process. And that's all this lesson is about. Okay, so this is a quick review of the normal distribution. First, the mean and the median are equal, which is to say half the values are below the mean and half are above. So the mean is like a 50% mark. The normal curve is bell-shaped and symmetric with respect to the mean, we know that. The total area under the curve is always 1. Normal curves extend endlessly in both directions, but are very nearly 0 for values more than around 4 standard deviations above or below the mean. The curve basically vanishes at that point. The normal curve changes its curvature from upward to downward, or vice versa, at 1 standard deviation below and above the mean. These points are called inflections, and that's only because it helps you guess the standard deviation. If you can find the middle and find an inflection just visually, you can guess what the standard deviation is. Okay, just the distance from the middle to the inflection. Okay, that's just a kind of a bit of trivia. Now, where we find normal probabilities, this is table A1, and we've already practiced this. Table A1 gives areas for which probability distribution? Not this one. This is a non-standard normal. Table A1 gives areas for the standard normal distribution. The key word there is standard. Which we usually use a z to represent standardized values, which means you've taken z-scores. Standard normal distribution is the distribution of z-scores. With, let's just say the mean is 0 and the standard deviation of 1 is 1 always for z-scores. Because when you take a z-score, you subtract your mean out, and then you divide by the standard deviation. So the mean goes to 0 and the standard deviation goes to 1. But the non-standard distribution is a normal distribution I'm going to say normal up on the last one as well. The normal distribution, but this one's normal distribution of values that we call x with mean mu. We don't know what the mean is anymore. And standard deviation sigma. Okay, so the first thing you'll do is you'll take z-scores to convert to convert x values to z-scores. And that'll be the standard normal distribution. You'll be working with z-scores where the mean is 0 and the standard deviation is 1. Okay, and there's a nice little graphic here sort of to depict the process. On the left, you have a non-standard normal distribution where the mean is mu. It could be anything. On the right, you have standard normal. Of z-scores, where the mean is always 0 and the standard deviation is always 1. So again, that's called standardizing because you're making everything the same. Every population becomes the standard normal distribution. Okay, and how do you take a z-score? With this formula. And that's how you convert a value of x to a value of z. Sometimes we need to reverse that and convert a z-score to x. So to convert x to a z-score, z is x minus mu over sigma. If you solve that for for x, I guess first thing is you'd multiply by z, or by sigma, like that, cancel. So you end up with z sigma is x minus mu, so you'd add mu to both sides if you're solving for x. And I think you end up with z sigma plus mu equals x. It's just it's sort of an inverse function. If you remember those from algebra. Okay, so score back to x. I think I'll use the form up above that x is the mean plus z standard deviations, because x is z standard deviations above the mean. Okay, little pause here. That's just it. Don't worry about the algebra. I'm going to minimize it literally. Okay. Looking to see if there are questions. I don't see any. Would you like to ask a question? I guess the only thing I would add is this area. And areas are the same as probability. That area is the same as the area that you have after standardizing. So maybe I'll say is the same as this area, which is also a probability. So while you're changing, by standardizing, you're essentially changing the numbers on the number line, but you're not changing the areas into the curve. Okay, so standardizing allows us to use a single tool for looking at probabilities for every normal population. A single tool, that would be table A1. So we standardize first, and standardizing preserves the area, which is the probability. You just look it up on the table. Okay, any questions? I guess what you really want to see are some problems. Right? So the standardizing process is you just convert x to z. So when you say that women's heights are normally distributed, the mean needs to be known. It's 66 inches and the standard deviation is 4 inches, okay? Suppose that x represents the height of a randomly selected woman, and we're gonna compute the following probabilities. Okay, so probability that x is less than 71.3, well, we're gonna standardize that and say z is less than whatever the z-score of 71.3 is. So down below, we have to compute that. Z formula is x minus mu over sigma. And so we're just going to keep using the mean, which is 66, and the standard deviation is 4. Those aren't variables. We need to convert that boundary point, the 71.3, to a z boundary. So we subtract the mean, which is 66, over standard deviation, which was 4. Shout it out or type it out when you get it. Maybe just once. Yeah, 1.325, thank you. Thank you, Wendy. So we say for x to be less than 71.3 is the same as z being less than 1.325. That's the process. We have to round that, so we better do probability that z is less than 1.33. Just remind you, the table only lets you go to the nearest hundredth, 2 places after the decimal. And that's going to introduce a little bit of error into the problem. Okay, but let's go ahead and look it up. 1.33, the table, I think I put another, oh look, I put another copy on the last page. So you can just slide down for that. We're looking at 1.33 here. And those of you with the TI calculators, I'm just gonna assume if you have a question, you'll ask. Okay, so I think I got it here, 1.33 for a z-score. The area to the left is 0.9082. So we can just write that down. This is 0.9082. And I'll maybe draw the table. We went down to 1.3 and over 0.03. And we saw 0.9802. That's the area to the left, which is what they asked for here. Maybe I'll draw the bell curve. There's really 2 bell curves, but I think I'll just tend to stick with Z just to keep it simple. And we were finding area to the left of 1.33. And that came out to 9082. Any questions? Let's do the next one, 59.6, but this one's a greater than. So right off the bat, the 59.6 needs to be converted. So z is equal to x minus mu over sigma. So we're going to convert the 59.6 to a z-score. Mean is still 66, and the standard deviation is still 4. Most of the calculators have fraction buttons, and if you're having trouble getting this, I think I'm just going to show you this one time. I like using the fraction buttons with complicated numerators or complicated denominators. So this calculator has a fraction button above the 7. That somebody was talking about a TI-30. I think it's in the same place, but it looks like n divided by d for numerator over denominator. Just press that. It makes a neat little template here for typing your fraction in. And I don't remember what it was. It was 59.6. Okay. 59.6 divided by 66 over 4. And nobody's put it in, but what I got is negative 1.6. So you guys agree with that? So you see, it's really nice to put it in as a fraction. That way you don't have to surround things with parentheses. It's just super slick. And that tool will get more and more useful as we go. Anyways, negative 1.6. I think. So that means that the z-score is greater. You just change x to the letter z. The greater than stays, and z is greater than negative 1.6. So you keep the sort of the form of that expression that you convert to z. Okay. Now this is a greater than problem. The table only does areas to the left, and this is an area to the right. So you're going to use a rule of complements on this one. 1 minus the area to the left will be the area to the right. And so when we look up that negative 1.6, remember it's negative 1.60, and it's negative, so we'll go to the other side of the table. And so like that. Remember, z is centered at 0, so the negatives are on the left. Okay, so let's look up that negative 1.60 real quick. I'll come right back to the, oop, it's down below. There it is. Okay, negative 1.60, it's just right there in the first column. Okay, any questions about how to use the table? I think it's 0.0548. Any questions? Okay, so now that's the area to the left, remember. So I have to denote that somehow in my little diagram. Let's put it in, put the number in first, 0.0548. So I'll just draw a little arrow to that, 0.0548. But what we want is the area to the right. And those are opposites. So the rule of complements comes in 1 minus 0.0548. Anybody? Yep, thank you, Wendy. Very helpful. 0.9452 is the answer. I don't like rounding these. We went through so much trouble to get some precise numbers here. I don't mind carrying 4 digits on this since that's what's provided. All right, any questions? I'm gonna do a little cleanup work and move things around just a bit. There's one more. So we did a less than problem, we did a greater than problem. Now we have to do an in-between problem. These are a little more work because you have 2 z-scores to look up. The variable right now is the endpoints of the interval that we're converting. So the first endpoint is 56.2. Subtracting the mean of 66. This will be negative because it's below average. Standard deviation is 4. The other interval endpoint is 68.5. Subtracting 66 and dividing by 4. Okay, I did the one on the right and I got 0.625, which we're going to round to 0.63. Anybody get the other one? Yeah, thanks, Bren. Negative 2.45. That does not need to be rounded. Terrific. All right, so then we have to do two tables. I'm going to make a little space here. All right, so I think I'll do the bigger one first. So 0.63. And then negative 2.45. Okay, so let's do the 0.63 first. Oops, it's down below. I keep forgetting. There we go. 0.63. So with the 0.63, I'm getting 0.7357. Okay, and I'll put that down up here, 7357. Okay, next one's negative 2.45. So let's do that. All right, so negative 2.4 and then 5. Okay, so I've highlighted that up on the screen. Any questions? So it's 0.0071. Let's copy that over. 0.0071. And then remember, when you're going between two numbers, you just do the big area minus the small area. So the big area was the 0.7357. Oh, wait. Let me put it into Z notation first. So the probability that X is between 56.2 and 68.5 is the probability that Z is between negative 2.45 and 0.63. I'll say 0.63. And again, big area minus small area, so that's 0.7357 minus 0.0071. Getting a little tight in here. Anybody? Yep, 7286.7286. Almost 73% chance of having a woman in that range of heights. Okay, any questions about that? We're almost done with this and we'll take our break. Okay, so this is just learning how to use the table, basically, and then we'll use this for quite a while now, basically till the end of the semester. We'll be doing problems like this. So this is an important drill that we're going through. It's just a drill, but you have to be able to do these probabilities for some of the research methods we'll be talking about. Okay, so let's go on. There's just a couple more here. The next one says, how tall is a woman who's in the 85th percentile? So we know how she lies in the distribution, but we don't know how tall she is. So this is like doing a problem in reverse. Where does she lie in the distribution? Is she below average in height or above average in height? Well, 85th percentile seems pretty tall to me. Remember, the mean is at the 50-50 mark, so that's the 50th percentile. She's taller than 85% of other women. Okay. Now this is doing the problem in reverse. So if we look up on table A3, A1, something close to 0.85, that would be the area to the left. Let's look for it. Oops. We'll clean up here. Okay, 0.85, she's above average, so her z-score is positive. There's an 8508. And 8485 is too low by 15 10,000ths, so that's no good. 8531 is obviously too big. So yeah, we're gonna go with the 8508. That's the closest one. And it corresponds to 1.04. That's the 85th percentile to the nearest hundredth. 1.04. So that's a z-score. Okay, so let me go back to the problem. What did I say? It was 8508, was it? Yeah. Okay, and that came out to 1.0 and 0.04. So as a z-score, we've answered the question. But that's not how tall she is. We just, we're real close because we know she's 1.04 standard deviations above average. And then I would just refer to the formulas that were at the beginning of this lesson. So let me go back real quick to that. Way at the top, we had, where did it go? Keep going. I think I went too far. It's here. There we go. All right. There it is. To convert a z-score to x, right there. X is the mean plus z standard deviations. No kidding. Because the z-score is the number of standard deviations above the mean. So x, her height, is x. That's the mean. Sorry. That's the mean plus z standard deviations, because she's always z standard deviations above the mean. That's what the z-score measures. I think the mean was 66, standard deviation is 4, so you have to take 66 and add 1.04 standard deviations, which are 4. That's it. Yep, thank you, Bren. 70.16 inches tall. That's obviously sort of an estimate. She's not gonna, we don't know exactly how tall she is, but we think she's pretty close to 70.2 inches, and even that's pretty precise and maybe overly precise. This assumes The population really is perfectly normal. Nothing's perfect. So these are estimates based on the best information we have. All right, this is another one. How tall is a woman if 35% of women are taller than her? We should draw that picture as well. So if 35% of women are taller than she is, she's still what I consider tall-ish. The area to the right is 0.35, okay? And the area to the left, you're gonna have to do 1 minus 0.35 to get, I think that's 65%. 0.65. Remember, you have to know the area to the left to get a z-score. Okay. And so going into the table, you're looking for something close to 0.65. Okay. By the way, she's taller than 65% of women, so that makes her 65th percentile. So let's just see if we can find a 0.65 here. It won't be exactly there, but we'll hopefully find something close. Now, see, I see a 648, which is a little low by 20 10,000ths. And then a 6517, that's better because it's only over by 17 10,000ths. So that's what we're going to go with. So, okay, so we're going to go all the way down. We see her z-score is 0.39. 0.39. Just like that. Remember, we need to, that's the z-score, so the big question mark. Z is 0.39. So however tall she is, she's 0.39 standard deviations above average. So her height is x, and that's the mean plus z standard deviations. So her mean is, well, the mean of women's heights is 66. She is 0.39 standard deviations above, which is standard deviations 4. Okay. So she's not that tall. She's really close to average, but she's above average, just a little. Okay, anybody? Yep. Friend, you're all over it. Take 67.56. Again, it's just an estimate under an assumption of a normal distribution. That assumption is usually pretty reasonable. So this is a reasonable estimate, no reason to think it's perfect. Okay, and that's how tall we think she is. I think I'll show one last thing here. And the calculator has an inverse normal command. So just real quick here. When we do these problems that are sort of in reverse, you have to do the inverse normal command. So in that same menu, second data distribution here, the last command down here is inverse normal. It's not really the last. There's a bunch of commands in there. Okay, you just give it the area to the left. Okay, I think it was 0.65. And we want to do, I want you guys to show me the z-score, so leave the mean at 0 and a standard deviation of 1. Okay, so boom, boom, boom. And just hit enter and you get the 0.39 that we were using. 385, but it's 39. Okay, that's how you run that. So it's the same value. The calculator is pretty cool, works well. So that's it for that section. We're going to go ahead and take our break. Let's do a break till 10:20.